Hi there, Ravens. It is time to talk about periodic trends for the second time this year. Okay, so this is part 9, very last thing, periodic trends revisited. Okay, when we talk periodic trends, let's start with atomic number and nuclear charge. Reminder, atomic number is the number of protons in a nucleus. And nuclear charge may be a new term for you, but basically it is the total positive charge due to the number of protons in the nucleus. So the nuclear charge of a helium atom is positive 2. The nuclear charge of a carbon atom is going to be a positive 6. Okay, how many protons there are? Okay, let's look at the periodic table. Periodic trends for atomic number and nuclear charge increase as you move from left to right across the periodic table, and they increase as you move down a group. Okay, so if the atomic number is increasing, the nuclear charge is also increasing. That one's pretty easy. Okay, next we're going to talk about atomic radius, and for your purposes the very best way to think about it is just size. So when we talk atomic radius, you're thinking size of the atom. Okay, and here is the actual definitions. Feel free to pause and write this down if you wish to, but I like to look directly at the periodic table. So here it is. Moving across the periodic table from left to right, let's stick with the elements. Let's just look in row 3, okay? So here's row 3. Keep in mind that we have 3 energy levels occurring in row 3. So as we move from left to right, okay, we are filling up the energy levels. We have, here's our 3s group, right? And our 3p group, our 3ds aren't even getting filled yet when we're in the third row. But our number of protons are increasing every time we move over an element. We're getting more and more protons. Yes, we're also increasing electrons, but those electrons are the same distance away. Okay, so let's see if we do this. Let me get a pen. All right, so if this is our nucleus, right, in row 3, we have 1 energy level. Here's, whoops, very badly drawn 2 energy levels. And we'll try to do this one a little bit better. There you go, 3 energy levels. Imagine those as nice, perfect circles, as they are in my mind. And no matter how many electrons we add, okay, no matter how many electrons we add here, they're all going to be added to this same third energy level for all of the electrons here in the third row. So we're not changing the distance away from the nucleus, but we are changing the number of protons. That nuclear charge is increasing as we move from left to right. Okay, so as you move, the atomic radius is getting smaller and smaller because those electrons, the positive charge, the nucleus, is pulling tighter and tighter and tighter around those electrons. Okay, so atomic size or atomic radius decreases as you move from left to right across the periodic table. Now, going down a group, every time you move down, you're adding another energy level. Okay, so row 1 has 1 energy level. Row 2 is bigger because it now has 2 energy levels. Row 3 has 3 energy levels. Row 4 has the 4th energy level, and so on. So every time you add another layer of electrons, you are increasing the size of that atom. Okay, hopefully that made a little bit more sense. Okay, periodic trends. Ionization energy. Okay, ionization energy is the amount of energy it takes to pull 1 electron away from an atom. Okay, the farther an electron is from the nucleus, the easier it is to pull it away. So bigger atoms mean lower ionization energies. So this is where we get a connection to atomic radius or size. Okay, larger atom, lower ionization energy. Okay, they are opposites. So let's look and see how that looks. Okay, as you move from left to right, atoms are getting smaller, nuclei are holding tighter to those electrons, therefore increasing the ionization energy. So if you look, these purple guys over here are very high in ionization energy. Okay, helium and neon are the noble gases. They don't ever want to lose any of their electrons. They're beautifully, perfectly happy with their S and P orbitals completely filled. Okay, fluorine is like, I only need one more electron and I can be just like them. And we're going to talk about this in the next unit, a little foreshadowing here. Okay, but fluorine isn't giving up its electrons either. In fact, all of these guys over here are pretty purple. Okay, moving this way, we're increasing in our green color. Okay, and we have pretty low ionization energies. Francium, cesium, here we're getting into our lowest of ionization energies. Okay, and if you look closely, you can see the numbers, right? Francium's at a 380, where fluorine is 1,681. And these are kilojoules per mole. Okay, but you can just look at magnitude of number. Okay, down a group, okay, hydrogen is a 1,312 versus francium's 380. Okay, again, small atom, electrons aren't very far from the nucleus, hard to pull away. Okay. All right, next is electronegativity. Electronegativity is essentially how strongly an atom attracts, or a nucleus attracts electrons to itself. Okay? In other words, how much an atom wants another electron or other electrons. Okay? Metals react by losing their electrons. Metals don't want their electrons. They are electron donors. They give them away. So by giving them away, they have a very low electronegativity. You can think of metals as like, hey, I have a sign up, and some of them say free to any home, take them, don't care, get rid of them. Whereas other metals are a little bit more peculiar, and they'll have a sign that says, okay, free to a good home. Okay, I'll give away my electrons, but I may charge $1. Okay, low cost, you get the idea, you'll see. Okay. Nonmetals react by gaining electrons. They want electrons, so they have a very high electronegativity. Give me your electrons. I love mine, and I love yours too. Give me electrons. The larger the atom, again, the lower the electronegativity. Okay, so let's look at the numbers here. Okay, highest electronegativities are over here. Okay, you may ask, why are these guys white? Well, we can't even get them to accept another or even share, okay? They're happy. They're so happy they don't give up theirs. They don't take another one. But these guys have been able to forced to do it. Okay? But here we go with fluorine having the highest of all electronegativities. Oxygen's pretty high up there, so is chlorine. Okay? Nitrogen, so small atoms that have electrons close to the nucleus, and those that are in need of just a couple electrons to fill up and complete their shell have a high electronegativity. They love electrons, whereas these guys over here don't. Now you may wonder about these guys in the middle. We don't really like, at this level of chemistry, we're not getting into why the middle ones, why some of them want to hold electrons and others don't. Okay, that's something for another time. Higher level class. Okay. All right, reactivities. Well, metals are more reactive as electrons become easier to remove. So the larger a metal atom is, the easier it is to lose its electrons and the more reactive it is. So big metal atoms are highly reactive. Nonmetals are more reactive. the higher their electronegativity. The smaller the atom is for a nonmetal, okay, the more reactive it is. So fluorine is highly reactive. It's very tiny, it's holding very tightly to its electrons, and it is just a voracious, I want electrons. Oxygen isn't so much different. Let's look at the periodic table, okay? So here we go. These guys over here are the nonmetals. The smaller they are, okay, and remember size decreases moving this way, okay, but it increases going down. So oxygen is actually a smaller atom than chlorine is. Oxygen loves electrons almost as much as fluorine does, and it increases their reactivity. Whereas moving over here, looking at the metals, as we move in this direction, our atoms are getting larger, okay? The electrons are farther away, and if they lose electrons, that's fine with them, okay? So they are also very reactive. They are willing to give up electron to anyone and everybody down here, okay? Up here, a little more selective. Here's a nice table showing the trends, and you can see that atomic radius is completely opposite of the ionization energy and electronegativity, and that is in both directions, okay? Atomic radius is the only one that doesn't increase or decrease, never mind. Scratch that, I wasn't saying that. All right, so we get that increase. I want to show you really quick the last picture. This is from your packet, and it does a really nice job. Okay, you can see the atomic size getting smaller and smaller as you go across the periodic table. You can see atoms getting bigger as you go down a group, as we increase the number of energy levels. Okay, then you can see the numbers for the atomic radius in picometers. So you can actually visibly see the numbers decreasing. Okay, notice oxygen's is a little bit smaller than fluorine's. Okay, oxygen's holding on to them just a little bit tighter. Okay, that's one of those oddities. We'll study that more in like a college chem class. Okay, and then we look at first ionization energy, the amount of energy it takes to remove that first electron. Okay, these guys on this side, outside of hydrogen, hydrogen really, really likes its electron, and it's like Mercury, right? It's right up close to the sun, right close to that nucleus. Okay, these guys, pretty good about getting rid of that electron. Over here, not so much. Okay, and again, electronegativity is the number down at the bottom. Okay, and wanting to keep and hold on to not only their own electrons, but everybody else's, whereas these guys are like, you want it, it's yours, please take it free. Okay, all right, so I hope that gave you a little bit more of an idea. Let me know if you have any questions. It's been fun chatting with you. Bye for now.